Ever wondered why K-nearest neighbors can seem so basic, even a little frustrating? Well, that's because KNN sucks until you learn how to unlock its full potential. In this video, we're going to take KNN to the next level by combining it with principal component analysis, turning it into a powerful tool that actually works. By the end of this video, you'll see how these techniques can completely transform your approach to data. And don't forget, hit that subscribe button so you won't miss out on more game-changing insights. We start by importing essential libraries: pandas for data handling, NumPy for computations, and matplotlib.pyplot with Seaborn for visualizing our data. We load the dataset with pd.readcsv. To understand the data, df.head shows a quick preview, df.columns lists all the features, df.shape reveals its size, and df.isna.sum checks for any missing values. Using value counts, we check the class distribution. We then drop the unnecessary column unnamed with df_drop. And use df_head to confirm the changes. We set the figure size with plt.figure. Then use sns.countPlot to visualize the distribution of the diagnosis column. The plot is labeled with a title, x-axis, and y-axis for clarity. And plt.show displays the plot. We visualize the distribution of diagnoses using a pie chart, which shows the proportion of each class in the dataset. The chart displays percentages for each slice, giving a clear representation of the class balance in the data. We use a kernel density estimate plot to visualize the distribution of the radius mean feature, separated by diagnosis. This plot helps us understand how the feature behaves for each class, with shaded areas to highlight the density of values for each diagnosis. We use a box plot to compare the texture mean feature between diagnoses, helping us identify differences in the distribution and detect any potential outliers between the classes. We calculate the correlation between features and visualize it using a heat map. This helps us understand the relationships between different variables in the dataset, with the color scale highlighting stronger or weaker correlations. We create a scatter matrix to visualize the pairwise relationships between selected features in the dataset. This visualization is useful for identifying patterns, trends, and correlations between the variables. The diagonal displays the KDE of each feature, which helps us understand the distribution. We use a violin plot to compare the distribution of values between diagnoses. highlighting the density, spread, and any differences in the feature's behavior across the classes. We convert the diagnosis column to numerical values, mapping M to 1 and B to 0 for machine learning compatibility. We split the data into features, X, and target, Y, with diagnosis as the target. We apply standard scaler to scale the features, transforming the data so that each feature has a mean of 0 and a standard deviation of 1. This ensures that the model treats all features equally and prevents bias towards variables with larger ranges. We split the data into training and testing sets, using 80% for training and 20% for testing, to evaluate the model's performance. We initialize the k-nearest neighbors model with 5 neighbors, k equals 5, and then train it on the training data using KNN.fit. This allows the model to learn the patterns in the data and make predictions based on the nearest neighbors during testing. And we make predictions on the test data using the trained model and store them in YPred. We evaluate the model's performance using classification report, which provides metrics like precision, recall, and F1 score for each class. We apply Principal Component Analysis, PCA, to reduce the features to 2 components, making it easier to visualize the data while preserving its variance. We split the reduced PCA data into training and testing sets. With 80% for training and 20% for testing, to evaluate the model's performance on the transformed data. We train the k-nearest neighbors model on the PCA reduced data to make predictions. We define the range for plotting by creating a mesh grid that spans the entire PCA transformed feature space. This grid helps us visualize the decision boundaries of the k-nearest neighbors model, showing how it classifies different regions based on the 2 principal components. We predict the class labels for each point in the mesh grid and reshape the results to match the grid's dimensions for visualization. We visualize the decision boundaries by plotting the contours based on the predicted class labels. The plot shows the decision boundaries with contours for each predicted class. The data points are overlaid, color-coded by diagnosis, to show how well the model separates the classes in the reduced feature space. We have successfully implemented the k-nearest neighbors algorithm for classification, reduced dimensions using PCA, and visualize the decision boundaries. In the next video, we'll dive into naive Bayes for classification. Stay tuned.